So welcome everybody to this new session of the bank seminar. Today it's our pleasure to welcome Sylvia Serfaty from Courant in New York, and she will talk us about vortex points and vortex lines in the Ginzburg-Landau model. So thank you, and go ahead, please.
Okay, thank you very much for the invitation. I tried to find a topic that connects vaguely to geometry. And I'm going to talk about vortex lines in the Ginzburg-Landau model. So this is a variational problem, very famous model from physics. In fact, the physics of superconductors and superfluids. So, you know, in superconductors at very low temperature, you have the phenomenon of currents that can flow without resistivity. And there's the Meissner effect, which says that the superconductor expels the magnetic field. And in fact, there's several regimes, but what will interest us in particular is the regime where you have vortices. So when Hx here represents the intensity of an external field. So if Hx is less than a first critical field Hc1, there is indeed this Meissner effect and there is no vortex. And when you pass Hc1, which is called first critical field, then you start to see these vortices, and then you see more and more as you increase the applied field. And in a sort of 2D situation, if you looked at a cut or at a thin film, then you would see these triangular lattices of vortices. In fact, they are called the Abrikosov lattices. Okay, and then you can continue increasing the field, and you get to other range of situations that are a bit less important for us. And as I said, this works for superconductors, but also models very close to models for superfluids, rotating Bose-Einstein condensates, etc. Okay, so for a long time, people studied a simplified model, which you may recognize. It's this model. It's like a Alenkane or Modica-Mortola energy functional, except that U, instead of being real valued, it's complex valued. Okay, so that makes a big difference. And here we think of it in 2D, in a two-dimensional domain. And the zero set of U then is points, right? Because it's complex valued. And these points are surrounded by, you know, if U vanishes, there's going to be a length scale here, which is this epsilon parameter here. So you're going to have like little disks of length scale epsilon in which modulus of U is small. And otherwise, modulus of U is very close to 1, because here it's very penalized to be far from 1. And in fact, it should behave like a harmonic map, like a S1 valued harmonic map away from these vortices. But what's interesting are the vortices. And so when you let epsilon go to 0, you will see these really point-like vortices in 2D. So if you want to represent what they look like, so think of so this is complex valued, think of a sort of trigonometric form here. Rho ei phi, rho is modulus and phi is the phase. So they are both real valued functions. And so the modulus will vanish with this sort of length scale epsilon around a point x naught. So it will be 0 at the origin and 10 to 1 at infinity. So you make like a, you know, a sharp sort of well. And what's interesting is that the phase phi can be sort of multi-valued, right? So when you integrate d phi d tau over a circle centered at the point x naught, because f of x naught is 0, this number doesn't have to be 0. It can be just a multiple of 2 pi, an integer multiple of 2 pi. So that is called the topological degree of the vortex. So if you want, it's the number of times you turn in the complex plane, you turn around 0. Okay, so the true vortices are those that are topological, that have a non-zero topological degree. And these vortices, they cost energy, and you can see that they cost at least an order pi times absolute value of degree times log epsilon of energy, where epsilon is this line scale. So if you want to see that, you write in this trigonometric form, or phase modulus form. Rho squared grad phi squared, you approximate rho by 1, at least in the complement of some ball centered at x naught. You can say that rho has converged back to 1. And then you integrate that by bounding it from below by the circulation, or the tangential derivative squared on circles. Whoops, sorry. And then you apply Cauchy-Schwarz in reverse. You bound from below the integral of the squared by the square of the integral, divided by the length of the circle, so that's the perimeter, 2 pi r. Okay, and then this, now you recognize the degree. So you have this integer, 2 pi d, and when you square that and you integrate all of that, you find a 2 pi d squared log 1 over epsilon. That's the leading order when epsilon goes to 0. So it's a divergent contribution. And it's carried sort of outside of the core. It is the energy that's in a far field. And at least you can bound from below by absolute value of d. So you see that the least costly is to have degree 1 if you're going to have vortices. Of non-zero degree, the least costly is to have degree +1, -1. Hence this energy cost. Okay, you can feel free to interrupt with questions. Okay, so on this simplified model, there was a lot of studies like 25 years ago. People assume that you're in a situation where you can bound the number of vortices. For instance, you have a Dirichlet boundary condition that imposes a topological degree equal to, say, capital N, fixed, and then you still let epsilon go to 0. And Betuel, Brézis, Hélin pioneered this study in a famous book. They showed that, among other things, they showed that if you take minimizers of the energy, the vortices will all be a degree +1, or all of degree -1 up to change of orientation, if you want. So this is what I was saying before. +1 seems like the least costly if you're going to have degree. And moreover, after this log epsilon cost for each vortex, there is a next order cost, which they call the renormalized energy. So this is what you obtain when you subtract off this divergent cost. And this is an interaction between the vortices. So the vortices will interact, and that's the next order in the energy. So it will want to minimize this interaction energy, which is at leading order, it's like a logarithmic interaction energy. So you see it's sum of log xi minus xj. Here the di's should be all +1 or all -1. So here you can replace by 1 if you want. And then there's some extra terms which are boundary terms. But important thing is vortices repel each other. They don't like to be too close. Vortices of same size repel each other logarithmically. It's also the Kirchhoff Onsager energy if you write it in the whole plane. Okay, so now comes the expansion of the minimal energy. We have this divergent part, pi n log 1 over epsilon. So it's, as I said, pi log 1 over epsilon per vortex, plus the minimum of this w, and then the rest is then a little o of 1 as epsilon goes to 0. Okay, so this is a rather simplified setting, right? Because as I said, you impose some boundary condition, and this way you obtain some non-trivial minimizers. They also showed that if you have non-minimizing solutions, vortices will converge to a critical point of W. You can even also show that if you have stable solutions, they converge to stable critical points. And then you can also try to do a sort of reverse, and this has been done a lot in the context of minimal surfaces, right? So the analog of this in the scalar valued case when you don't impose U to be complex value but real valued, you converge instead to interfaces, which are hypersurfaces, if you want, or in the sense of currents. And so people have asked the same kind of questions. If you give yourself a minimal surface, can you find a critical point to Alencane that converges to that? And so this has been done also in this context of vortices. Okay, so now what we want to study here is not the simplified Ginzburg-Landau energy, but it's the full energy of the physics, which comes with a gauge. So that's the main difference. Instead of having just a U, you have also a gauge field A, so it's a vector field. So this is, there's quantum mechanics reasons why this should be the right energy. And now we want to work also possibly in 3D. This is the physical setting, right? In a bounded, simply connected domain. So we have the same things that before, complex valued U, but now we have this vector potential A, and the gradient sub A is the covariant derivative, which is gradient minus IA. So this is like a gauge theory, but abelian. It's only, the gauge group is U1. And you have other quantities here, H, which is the magnetic field, just like in in physics in Maxwell's equations. So it will be the curl of A. A is the vector potential of the magnetic field, and Hx is a vector field, which is the applied magnetic field. So we'll assume it has an intensity little hx, like before, that we can tune. And then there is some fixed vector field, h0x, that we don't touch. Okay, and then you still have the epsilon as before. And epsilon will be considered very small, and it's physically relevant to take it very small. There are some equations associated to this functional. They are a little bit more complicated. They come with a gauge again. You don't have to read them so carefully. And as I said, you have these gauge transformations, which are U1 based. So if you change U to U EI phi and A to A plus gradient of phi, the physics doesn't change. So we have to work with physical quantities, which are gauge invariant ones. So two quantities we will look at a lot are the supercurrent, which is defined like this. So you make a complex product somehow between this complex number and this vector, this complex vector field. So in complex representation is defined like that. And what we call the vorticity, which is the curl of that current, plus the magnetic field. Okay, so that seems a bit, maybe a bit difficult to remember, but we will come back on these quantities. So the problem for our situation is that now we don't have vortices imposed by the boundary condition. Instead, it's the H external that's going to drive the vortices, and their number is going to be unbounded when epsilon goes to 0. So if H is large enough, there's going to be more and more vortices. So you can't have an a priori bound. And so a lot of the calculations, at least the one that I was showing you before, this little toy computation, doesn't work so easily when you start to have many vortices packed together. So there are some techniques that are due to Sandier and Gérard in the late 90s called Vortex balls construction that allow to estimate the cost in an optimal way, the cost of possibly many vortices that could clump together, could have pluses and minuses clump together, etc. So that's one first difficulty, the unbounded nature, a priori at least, of the vortices, of the number of vortices. And the second difficulty is that if you want to work in a 3D setting, which is physical, then the vortices become curves. Instead of having points, you have lines. And a priori, these curves have no regularity. There are like the limits of the zero set of something, but you have to understand them to describe them in the framework of currents and use tools from geometric measure theory. This is the only way you can deal with things that can be so rough. Right? So instead of paying the price pi d log epsilon per vortex, which was the price in 2D energy cost, it was quantized. Now the price is going to be pi d times the length of the curve. So this is denoted like that, like the mass of the current gamma. So you have to integrate the cost along the line. So you pay the length, and that's no longer quantized. So that's important. And so the people have worked on developing tools to describe this precisely with these GMT ideas. Okay, but usually it was not done for the full model. It was for the simplified model without gauge. Okay, so I go back to the vorticity, which I defined before, and the current.
Excuse me, Sylvia.
Yeah.
One question. D is, again, the degree of the vortices. What does it mean in 3D?
So in 3D, you have a curve, right? And basically, if you look at one loop around the curve, you can count the winding number, and it's going to be constant along the curve. So it's like the degree of any slice. It's the same. Right, so think of your curves as being just straight lines for now, and the 2D section is the previous situation. Thanks for the question. Okay, so to see what the current does, we're going to do it in, again, this trigonometric or phase modulus representation. So J, you can just read it as rho squared times grad phi minus A. So here A is the gauge. If you don't like the gauge, just take it 0 in your mind. And mu UA. So you see, it's like the gradient of the phase, and you can think that rho is like 1. So whenever you have a phase that turns like a vortex, the current turns. So it turns around the vortex line. There will be a picture in a minute. And then when you take the curl of that thing, so formally you're like taking the curl of the gradient, because you can equate rho to 1. And here you see the definition has minus A plus A. So if you take the curl of a gradient, in principle you get 0, except here it's not a gradient of a true function, it's a gradient of a function that has a that is a sort of multi-valued. Like it's like the polar angle theta, right? If you take gradient of theta, that's not a true gradient, and in fact it will pick up a Dirac in the sense of distribution. It will pick up a Dirac at each vortex center. So every time you have a vortex at AI with degree di, this is just picking up the vorticity is just carried precisely there. So it's perfect. It measures where you have vortices. And there are some estimates that make this, okay, so here there's an approximation, right? And you can make this quantitative as epsilon goes to 0 through something called Jacobian estimates, which I won't give details. Okay, so now we have the Ginzburg-Landau equations, and one of them is actually Maxwell's equation that relates magnetic field to supercurrent. So the curl of the magnetic field has to be equal to the current J. It's always like that. And if you take the curl of that equation, you find an interesting linear elliptic equation, which tells you that minus Laplacian of the magnetic field plus the magnetic field is equal to the vorticity, because mu is the curl of J. Okay, you find this. So in fact, there is just a direct linear relation between vorticity and magnetic field. And then you can see that this very important part of the energy becomes roughly equal to gradient h squared, which you can express in terms of the vortices through some sort of Green's function representation. Okay. So this is how you can guess that there's going to be this logarithmic repulsion in 2D because the log in 2D is precisely the Green's kernel. Okay, so let's look at the picture as I had promised. So this is a vortex schematic picture. Here it's rather straight, but it doesn't have to be straight. Right, so in the middle, U vanishes. Outside this tube of length scale epsilon, modulus of U will be almost 1. So you can think of it as 1. The supercurrent J is turning around when there is a degree. And the vorticity mu is precisely carried by the vortex tube in a direction. So it's a current, in fact. It has the direction of the vortex. Okay. So in 2D, the situation of the 2D model with magnetic field, with the gauge, with this external field was studied some time ago now by Sandy and myself, and we rigorously proved this whole picture, basically, which is that when you're below HC1, indeed, it's as predicted in physics, right? You have the Meissner effect, no vortices, modulus of U is like 1, nothing happens in some sense. And then you reach HC1, and we show it's some constant depending on omega, times log 1 over epsilon. So that's the value at which the first vortex appears. So asymptotically, it's like that. And then you can start to see a second vortex and a third vortex every time you increase HC1 by an increment which is like log epsilon. And then eventually there's so many vortices that they start to have a number that is unbounded with epsilon. So their number becomes proportional to log epsilon, really. And you describe the region where there are vortices through a free boundary problem, which is actually an obstacle problem, a standard problem in the calculus of variations. And eventually you increase further the magnetic field. The region with vortices takes up the whole space, right? It takes up the whole domain. And then you reach the second critical field. So this is what we showed, right? That this can be made rigorous, and we derived an interaction energy, which is the logarithmic interaction plus some form of confinement that keeps the points sort of centered near the center of the sample, whatever that means. Okay, so then our goal was to try to extend this picture to 3D, where, as I said, you have all these additional difficulties. So for the 3D problem, okay, first, if you neglect all these magnetic effects, you remember a vortex line costs a price proportional to its length, right? So length times log 1 over epsilon. So in principle, if you look at minimizers of the energy, they should try to minimize length. So they should be straight lines. Maybe there's some boundary condition, again, that forces you to have these vortices in the first place. But once you know what's happening on the boundary, then you should just connect the dots with straight lines or currents, which in retrospect will be just straight regular lines, or things that are called minimal connections. So there was a lot of work to prove that in the turn of the century. And that was always for fixed number of lines, right? There was a formal paper after Lyon and Rivière that started to derive this competition between length of vortices and logarithmic repulsion, because the length is the leading order, but in principle these lines should also interact, just like we saw the vortices in 2D interact. So there should be some logarithmic repulsion somewhere, but it's not easy to extract it. Okay, then there was several works to do this approximation of vorticity based on Federer-Fleming. Okay, maybe I will go a bit fast on that. And the construction that we use the most in our work is by Carlos Roman. he made a 3D vortex approximation construction, which is quantitative. So what it does is you give yourself a U epsilon, U depending on epsilon, with some control on its energy, and you construct a piecewise affine object that approximates its vorticity to good order with a quantitative approximation. Okay, so in principle, the vortices could be really nasty for general configurations. If you don't have a PDE, you don't know that there are minimizers. You could have many loops. You could have many like little things that are structured that is useless in some sense. And what you want to do is you want to clean it up and to approximate it by polyhedral lines in such a way that you're not making a big error on the vorticity. So that is what the construction is doing. Okay, so this is an equation for what I was saying, right? The vorticity mu of UA, you will approximate it by 2 pi times the sum of polyhedral currents, and the energy will be bounded in terms of the mass of that current, which is this approximation thing, up to some quantitative error, which is relatively small, relative to the leading order log epsilon. Okay, so now if you want to understand when vortices happen, they happen near this first critical field HC1. And okay, we have to do a little computation to understand when HC1 is or what its value is. So there is some particular magnetic field B0, which is the one that you find when you just set U to be equal to 1. So the Meissner solution is the solution that's trivial in terms of vortices. It's just U equals some constant of modulus 1, so we might as well take U equals 1. And when you plug that into the Ginzburg-Landau equation, you find a certain equation for the magnetic field. Okay, and that's the equation for the magnetic field. Again, don't read it too carefully. And what you find is you can split the energy, and that's really crucial in some sense, between some part that is the energy of this Meissner state, so it's some sort of constant, some new energy, which I will describe, and some coupling between the vorticity and the B0 field. So this F epsilon of U prime A prime, so U prime A prime are just like U and A, except you've sort of gauged out some part of it. And F epsilon is just like the Ginzburg-Landau energy, but without Hx. So just set Hx equals 0. So it's the same thing. It will see the price of creating a vortex. And that price will be like pi times log epsilon times the length. Okay, so here you have a constant. Here you have a thing that pays the price of the length, plus maybe interaction between vortices. And then the third term is a magnetic coupling, which is the thing that makes vortices interesting. Because otherwise vortices, we know that they cost energy. Why would we see them in the first place? Because this term becomes negative and so becomes much smaller, decreases the energy when there is vorticity. So if mu of UA is 0, this term is not there. But if mu, the vorticity, is not 0, you can see that it's interesting to align the vorticity with the B0. You see this wedge product favors mu to be aligned with B0. And so if Hx is large enough, this term can start to balance out the cost of a vortex. And when you do this balancing, this is how you find the value of Hx that you should find. So okay, so this is the cost, as I said, 1/2 times the mass of the vorticity. So mass of the vorticity counts the 2 pi times the length. And it will be favorable if that. And when you put all these together, you find that okay, so HC1 will be proportional to a constant times log epsilon. That's the thing that makes these two things basically balance each other. And what is this constant? Okay, so this constant is derived in terms of this B0 as before. and you want to maximize this ratio, which we call an isoflux problem. So here you want to maximize this vector product of the vorticity with B naught. So as I said, it's like trying to align with B naught. And you divide by the length of the curve or by the mass of the current. Okay, so it's really a bit like an isoperimetric problem. Because an isoperimetric problem, you're trying to maximize area given a length. So here you're trying to maximize flux given a length, but it's similar in nature. Okay, so if you find the maximum of this, it gives you the constant, and if you find the maximizer, it's what we call gamma naught. It's an optimal curve that achieves the supremum. So we prove that if P0 is nice, this supremum is achieved, and it will be achieved by a simple curve with no loop and two endpoints on the boundary. For instance, so you can think of a very simple geometry, which is the geometry of the ball of something that's spherically symmetric, and an applied magnetic field which is vertical. Then the gamma naught is just simply the axis of symmetry, right? The axis of rotational symmetry. That's where the vortices will. And then we need to understand also, if this maximizer is regular, if it's non-degenerate, but that's more difficult. Okay, so from now on, we assume that there exists a unique curve that achieves this max. And we also assume this form of non-degeneracy, which is that if you look at other curves that don't achieve the max, you can bound from below in terms of a certain weak norm of the distance. Okay, so this non-degeneracy that we will assume, we can prove it at least in the case of balls, when, as I said, the vector field is vertical and if the ball is of small enough radius. Okay, so this was proved that this HC1 is indeed the correct value of the critical field. Carlos Roman showed that if you are below that, then you have no vortices, and if you're above that, you'll have vortices, and this is the approximation of HC1 up to a log epsilon error. And now what we proved is that if you don't exceed HC1 0 by more than log, then the vorticity will remain bounded. So you see, when you pass the threshold HC1, it starts to be interesting to put one vortex. But in principle, if you put one, why not put 2, 3, 4? You could have multiplicity of vortices in the same location. But the thing is that the vortices repel each other. So in fact, they don't like to be on top of each other. And that's what prevents from having too many of them come at once. So this is what we show, is that if you are not too far above HC1, you will actually still control the number of curves that comes in. So this is this theorem. So here is a picture. So as I told you, if you're in this type of geometry with rotational symmetry and a vertical magnetic field, then the gamma naught you can prove is just the rotation axis, the axis of rotation. And so you see what you're trying to maximize here is the flux gamma naught B naught. It's actually like computing this area in some sense. Okay, and when you increase the magnetic field, so the vortices will come at gamma naught, but if more and more appear in the sample, they try to separate a little bit because they want to be near gamma naught for magnetic reasons, but they repel each other. So the effect of that repulsion is that they move apart by a length scale which is like 1 over square root of hx, and that's not obvious to determine. But this is a very small length scale, in fact, because hx itself is like log epsilon. Okay, so this is the picture that we, wanted to prove. And it actually matches quite nicely some things you see in simulations of rotating Bose-Einstein condensates. So you see these vortex lines. In particular, what you can see is that the curves are going to go to the boundary perpendicular, because at leading order near the boundary, the effect that matters is they want to minimize length. So, remember, they want to minimize length, they also want to maximize magnetic flux. But so as they get towards the boundary, they curve in order to reduce the length. And that is a phenomenon that is a bit contradictory to what was the expectation at the beginning of the story, because people just thought, okay, the leading order is the length, the curves will be straight. And the question is, is the magnetic effect enough to curve the vortices? Well, it turns out that it's just the length effect. If you don't have a directly boundary condition, your curves are free. And they are free to exit the domain the way they want, and the way to exit that minimizes length is, of course, to be perpendicular. Okay, so what we provide is a more precise description where we have the length of the curves, the interactions between the vortices, which I told you is logarithmic, plus magnetic confinement effect. So it's these three things that have to play together. But that is difficult because, the length of curve plays at order log epsilon, and the interaction between vortices is a lower order effect. And if we want to see that interaction, we need energy estimates with little o of 1 precision. But the tool that we had, which is the construction of Roman, it gives the order log epsilon error, so that's much bigger than little o of 1. So in principle, the approach doesn't seem very promising. But, okay, there is something that saves you, and maybe I'm not going to give too many details, but the idea is to do an anisotropic rescaling of the problem. So you're going to use gamma naught as an axis, and you're going to use tubular coordinates that follow this gamma naught. So if gamma naught is vertical, then it's easy, it's the vertical axis, but if not, and then you're going to make a rescaling in the direction perpendicular to this gamma naught. And that is going to give you, to allow you to retrieve the precision that you were missing in that direction, and that's the direction where interesting things happen. So you see, this is the situation. On the left, you zoom horizontally, sort of in the direction perpendicular to gamma naught, and then you try to take the limit as epsilon goes to 0 of this picture. So in the limit, you will see curves that are well separated, and you will retrieve the precision of energy that you need. Okay, so I can give you the statement of the theorem now. So we have gamma naught, which is assumed to be a unique maximizer of this ratio, this isoflux problem. And we call minus q its Hessian. So because this is a maximizer, the Hessian at the maximizer will be negative. Okay, so minus q will be positive definite. We assume it's positive definite. And we define, so given n, a number of curves, we're going to describe the curves in the frame of gamma naught. Okay, so that's the frame of gamma naught. So ui will be these vectors that correspond to the, the position of the curves in that frame. It's a sort of curved coordinates. Right? And we define an energy, which is going to be the total interaction energy of the curves. It's going to contain q of ui, so the Hessian of the isoflux problem, of that function r, that you multiply by the length of gamma naught, so that's like a constant. And here you see you integrate along the curve the logarithmic interaction between the position of the traces of the curves. So that's the logarithmic repulsion between the curves, and it gets written in a certain metric g that's associated to these tubular coordinates. So if everything is straight, you just integrate log ui minus uj, right? So the picture is like this. These are the ui's. So this, in fact, contains exactly what we wanted, which is it contains the logarithmic repulsion, and it contains the length and magnetic effect in the form of the Hessian of this problem. So it contains the corrections, if you want, to that effect. So then what we proved is that just like in 2D, so it's the counterpart result in 3D. So if you reach this field H1, so when n equals 1, this is 0. So if you reach 1 over 2 min r, it should be max r, sorry, log epsilon plus here some constant, you will have one vortex line. And then if you add, if your intensity hx reaches h2, you will have, so h2, you will have added 1 log to the intensity, so it will be like log plus 1 log, right? So if you add 1 log to the intensity, you will have 2 lines, and if you add 3 logs to the intensity, you will have 2 lines, sorry. Okay, so anytime you pass the n minus 1 log, you have n lines. So you add the lines one by one, and you will describe your vortex polyhedral approximation only by good curves. There will be capital N of them. And if you take these polyhedral approximations, gamma I, and you rescale them horizontally by the right factor, which is square root of log, then they will converge to curves which minimize this particular Wn. Okay, so if you want to see this, there's a limit problem, which is a geometric problem that contains these interactions between these curves, logarithmic repulsion plus magnetic length effect. And in order to see minimizers of this interaction problem, you have to take your actual epsilon curves, rescale them, just like in this picture, and take the limit as epsilon go to 0. So when epsilon goes to 0, they will converge to minimizers of this problem. Okay, so this sort of elucidates the behavior of the vortices when you are near the first critical field. And when you increase further the magnetic field, you will have many curves. So it will have to be described in an average sense. And that was done by Baldo, Gérard, Orlandi, Sonner. So it's much less precise what you obtain in that regime. You don't need things that are as precise as this. So I show you again the picture, right? So this is the gamma naught. This is the length scale, 1 over square root log epsilon of separation between the curves, which is relatively small. And with these curves coming out perpendicular. So this is the simplest geometry you can think of, which is, this has this rotational symmetry, but okay, our framework is meant to allow for possible curved situations where gamma naught can be curved, and then you have to work in these curved coordinates. That makes everything a little more complicated, but it works as well. Okay, so I think this is all, and I'm happy to answer questions.
Okay, thanks a lot, Sylvia. So let's see if somebody in the audience has questions. Well, in the meanwhile, I can ask one.
I have a question.
Okay.
Sorry.
Mm.
So you said that when the intensity increases, then you will get something similar to the 2D case. Some region which has which becomes a free boundary problem.
Yeah.
Is that what you expect in 3D or not?
Yes, yes. Actually, it was even shown by Baldo, Gerard, Orlandi Sonner. So it's a more complicated free boundary problem because it's kind of vector valued at the same time. I think I have a brief mention of it, but it's in that paper. So they're able to write a sort of analog of the free boundary. You should think of it as an obstacle problem or as an equilibrium measure problem in 2D. So it's a problem that's very analogous to the equilibrium measure because you have a logarithmic repulsion plus a price for the mass, right? So it's a sort of minimizing logarithmic interaction among probability densities once you normalize the mass. And there is a sort of vector valued analog of this in 3D because it has to be for currents. And they're able to identify this problem, but not completely solve it, I would say. They have some characterizations of minimizers, but it's a bit, yeah, it's less classical. But yes, you expect something like that. Something similar like that.
And related to this, in the 2D case, do you have regularity for the free boundary problem? Or?
So in the 2D case, you have exactly what is known for the classical obstacle problem. So you can branch, you know, Caffarelli's regularity results, basically, like all the results you know on. It's really a classical obstacle problem with a constant obstacle. So you
but
will
the
have
obstacle becomes in this case, which is the obstacle now?
Okay, so what you there is a duality, in fact, between the problem that we derive here. It's a convex minimization problem and the obstacle problem. They are convex duals of each other. And if you want to know what the solution is, you should take the following problem: minimize integral of gradient u squared plus u squared. Okay, with u equals what is it? 1, yeah, u equals 0 on the boundary, and no, you should not take that. You should take u equals 1 on the boundary, and u bigger than some constant lambda everywhere. So it will make like a flat obstacle. U is bigger than lambda is a flat obstacle. U equals 1 on the boundary. But because you penalize u squared, u wants to, it's more interesting to be close to 0, right? So it's trying to reach 0, but it has to be above a certain obstacle. So it will do like this and then flat, depending on the value of lambda. I have some pictures with that somewhere. I don't know if I can find them right there, but and that's yeah. So that's the standard obstacle problem with constant obstacle. And you will have the classification for regularity that you have for the classical obstacle problem. There can be cusps, and there is a small regions, small number of points where you can have cusps, but otherwise it's C1 alpha. You have exactly the same. Do I have any old slides where I have that? I don't know. It is it's hard to find. Anyway, yeah, so this is You know, I don't have it in like ready like that, but it's a very simple obstacle problem.
Okay, thank you.
Any more questions? Let me ask one. What is known about this Ginzburg-Landau model in a curved setting? In two senses. Or if you consider omega instead of a bounded subset of R3, for instance, a closed surface, or if the magnetic field is also subject to gravity effects. I'm considering the problem instead in R3, like on space-time, for instance.
Yeah, okay, so I think I can tell you what has been studied. I think it's natural to look at problems on a manifold, and people have looked at it. So instead of looking at the integral of grad u squared, you take a gradient sub g, right? And in the PDE is a Laplace Beltrami operator associated to your metric. And of course, as you can expect, the microscopic structure is not going to be affected by the metric, because when vortices get very close to each other, things are almost flat, and so you will have still the logarithmic repulsion, but it will be more like a Green's function of your manifold. That will be the type of interaction. So people have studied. I would say they have done the sort of finite number of vortices analysis, the analog of Bétuel-Brézy-Célin setting, where you have just the U, no magnetic field, and a finite number of vortices, and they're able to derive these things quite precisely. So there are some, the most recent papers I can think of are by Ignat and Bob Gerard, where they did that very carefully. And we had to use some things like that, because when we find ourselves in a curved geometry, in fact by accident, because we want to follow the curves here, and so when we slice, because we have to do two-dimensional estimates on slices, once we slice, we find ourselves with a metric, in fact, a natural metric induced by the coordinate changes. And so we use some of these techniques and some of these computations. Now, in terms of your second question, I think which would be doing a magnetic field in a geometric setting. I don't think that's been looked at. But yes, I think, and doing all these kinds of potential theory, equilibrium measures, logarithmic interactions on manifolds is actually a natural thing, and some of it has been done. A lot of the analysis should be sort of the same, or in terms of the results should be kind of the same, but you still have to carry out the stuff on the geometric setup, and that induces difficulties.
Well, so anything else?
Hi. So I want to ask question in 3 dimensions. So for the curve, have you some geometric description for this curve? For example, in the hyperbolic matrix, we know that the geodesic is perpendicular to the boundary. So could you give more information about this curve? Is some kind of geodetic for some metric?
Yeah, I mean, this is the thing you want to minimize. It's if you have a unique curve, you mean the one with just the gamma naught? So this is when you have n curves and you have the interaction, and if you have just one curve, you want to just maximize this R. Where is it? You just want to maximize this. Yeah, I don't know if it's really a geodesic. Maybe you could write it like that. The problem is it's a minimization under constraint, right? Because you normalize by the length. So it's a kind of, again, it's like an isoperimetric problem a little bit. You could try to write an equation for it and describe it more precisely. In fact, when we wrote that paper, we tried to advertise this problem as an interesting geometric problem on its own, for its own sake. And we would be very interested if people could solve some of the open questions. In particular, can you make a regularity theory for that maximizer, and maybe describe it better as a kind of, as you said, some kind of geodesic in some sense. But it's open. The problem, it doesn't necessarily lie in a plane, right? It could be really it's really a 3D curve. But yeah, these are interesting questions to analyze this thing more precisely. You can look at the paper.
Okay, thanks.
It has isoflux problem in the title.
Okay, thanks.
Any more comments? Well, if not, let's thank Sylvia again for the wonderful talk.
Thank you very much for the invitation, and good luck with your seminar.